Alrighty, so hello and welcome. Howdy. Guten Abend, good day. Happy Lord's Day. Praise God. Suddenly thought I should read my Bible more. I should probably be reading my Bible more. But I wanted to return to this question, this problem. Excuse me. Oh boy. Yeah, I was supposed to look at this yesterday, but I don't know what happened yesterday. I fell asleep during the middle of the day, and then I couldn't sleep at night, and I was messing around with all kinds of stuff, and for some reason, I didn't want to stream, I guess, later in the day, or I didn't want to stream when I was too tired to think, I guess. Something like that, I don't know what happened, I don't know what I did. Or, I don't remember what happened, but any which way, coming back to this problem, I have two ideas that may or may not be useful in approaching this problem, so we'll look to explore those two ideas. One of them I know is correct, but probably not efficient enough. I'm fairly certain is correct and probably not efficient enough. The other one is efficient, but maybe not correct. So we'll see where we get with those two. Yeah, so let's do that. So here we go. Problem again is ones and zeros. Given an array of binary strings, and two integers m and n, return the size of the largest subset of strings such that there are at most m zeros and n ones in the subset. A set X is a subset of a set Y. Elements of Y, X are also elements of Y. So we're going to select some of these strings in order to maximize the number of sets that we use, and we don't want to use any more than m zeros and n ones. And they have some examples. So you have 10, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, m is 5, n is n. So you want no more than 5 zeros and no more than 3 ones. So one choice would be 1, 2, 3, 4. Yeah, so 1, 2, 3, 4, 5. Excuse me, 1, 2, 3, 4, 5 zeros and 1, 2, 3 ones. So that's exactly what they say here. Most 5 zeros and 3 ones. There you go. 1, 0, 0, 0, 1, 1, 0, 4. Smaller subsets are these ones, and then there's an invalid subset with this in there, but this has too many ones. So anything containing that element would not be correct. And similarly, 1, 0, 0, 1, 1, 1, you would pick a 0 and 1, get 2, largest subset. So my thinking, the first approach is actually, I'm going to delete all of this too, because I don't think any of this is correct, what I did here. Also, I'm surprised this one took so much time. I think that was the problem I was looking at. Oh no, it's wrong. No, I'm sorry. And we figured out why it was not terminating, but I don't think it's correct. This idea was to just grab, I think we sort by size. Excuse me, or we sort by, depending on what we're looking for, we optimize at each step for the, if we have more zeros, then we optimize for something that has more zeros in it. If we have less zeros and more ones than zeros, then we optimize for something that has more ones. I think this is incorrect. Yeah, it's just wrong. I have a better idea. I have a different idea, hopefully better idea. And I think we're just only going to keep this binary values here. And what we're going to do is we're going to create a vector. So here's one idea. This is a little bit easier to program, I think. So let's see how it goes. But we're going to create a vector of these pairs of integers. Excuse me, just call it v. And we're going to say for const standard string s in strings, we're going to v.pushback count binary values of S. Now we're going to sort comparator function. We're going to sort on these pairs. And what we're going to do, whoa, is we're going to say, so this is interesting, right? We have a double Y proportion. And this is going to be, X's are going to have a value of 1 each, and Y's are going to have a value proportional to X dependent on the ratio of N to M. So, times M is the number of zeros, and you divide that by the number of Y's. And that should give us, this is not integer division, this should be, I don't think I need to do both of these. We're going to cast Y to a double and cast M to a double as well, and take a fractional, floating point. Use floating point arithmetic to find this proportion. And the reason for this is that if we're trying to get a subset with, so the rationale for this is like, it goes like the following. So if we took this problem and we simplified it to just one dimension, in other words, you can kind of consider this problem as two-dimensional. There's zeros and ones, but they're only zeros or only ones. It sort of would be like one-dimensional. And in that case, actually, the greedy algorithm is really straightforward, really simple. You could just sort by the number of zeros or the length of your string, really, and you would pick up as many of the shortest length, lowest cost sets as you can. So it would just be sort of left to right in sorted order, pick up one at a time, and you would pick those up until you have exceeded the target that you're looking for, or right before you exceed that target. So as long as you don't exceed the target, you'd add the element, and you just keep adding elements, and that's it. That's how you solve the problem. You can do it in n log n time, pretty straightforward, and that works also for the ones as well, same deal. Now, the problem with zeros and ones, you can kind of generalize that idea a little bit to like, okay, there's a certain cost in terms of resources to adding each subset. What would the cost function look like? So it's really simple when you only have one element, it's just the length of the string. But when you have two different elements and two different sort of resource pools to pull from, the question becomes, well, how do I have an accurate cost function for that algorithm? If I were to use that same algorithm, I should need to have an accurate cost function. And these other ideas that I had were kind of like grasping at that without actually directly addressing that, and they weren't very good heuristics for that cost function, or very good ideas. I think the cost function we can use is actually use the proportion of m to n. So if each x value is just worth 1, right, just a unit of 1, each x value is just a unit of 1, so the zeros are just units of 1. And if you had like 1x and 1,000 y's, the y's would be worth 1,000 to 1 of the x's. So the y's would be worth a lot less. So you'd have 1 over 1,000 for each y. If it was 1,000 x's and 1 y, it'd be the other way around. The y's would be worth about 1,000 times more than the x's. That's kind of the idea, is that we're considering like a cost function and amount of resource that we're starting with respect to m and n. So in order to properly evaluate what the relative value of each set would be in terms of resources, we want to assign a number to those sets based off of how many ones and zeros there are and how many ones and zeros we can afford. So that's kind of the impetus, the idea. So we have this y proportion here, or this, I call it y proportion, but we can call it ones proportion. It's probably better. I was using x's and y's in my thinking before. I was like, where zeros were x's and ones were y's. So forgive me for that if that was a little confusing where I was coming from with x's and y's. So the ones proportion we're going to say, and then we would say your return. So there's actually another function we would say cost evaluation, and this is going to be and I kind of would want to inline this if I can. I don't know if I can do that. And you're going to say return x dot first plus ones proportion times x dot second. Right, and this is going to be return cost of A is less than cost of B. And actually we can just inline it right here, I think. That's fine. And again, these are doubles. So everything converted to doubles. Hopefully this makes sense. Maybe I should have used an inline function. Yeah, we'll go back to that. It's fine. And everything's a double. Okay. I don't think we're going to need that much precision with the things we're looking at. Excuse me. So now we can standard sort proportionally on V. And now, just like the other algorithm we had, the greedy algorithm, we can just take elements from left to right until we can't fit anymore. And I think that would be our that would be the approach. That would be the solution. Now, is this correct? I have no idea. Is this going to work? I don't know. Maybe. Hopefully. We can actually do. A. What do you call it? We can do our destructuring right in the loop. Which is kind of neat. As long as m is greater than or equal to 1s, and actually it's the other way around, it's 0s, 1s. All right, then we subtract zeros. That's it, and you do it this way. And you don't terminate early because you could be in a situation where like you have 1,000 x's and 1 y, and so all the y's are towards the end, if there's any at all, and you could add a whole bunch of x's and sort of reach a limit where you can't add any more x's, where all the strings to the left side are just strings of x's. I'm saying zeros, x's, zeros, you have 1, 1 that you can have, and you have 1,000 zeros you can have, and so you have strings of all zeros to the left side, and then at some point you start seeing ones in the strings. Well, you could be in a position where even though you can't add any more of the zero strings, past that to the right, there's somewhere in there a 1 string that you can add in there, and so you don't want to terminate early when you do this. sort of TLDR. That's sort of an example where it wouldn't work. Would not work properly. Let's see if this compiles. Let's start with that. There's always something that I miss. Always something. Attempted too soon. Okay. Fair enough. Wrong answer. Oh, wow. So much for that idea. That's like nowhere near. Actually, the other idea was better. The other idea was closer. Really. Actually, when they're equal to each other, proportion of 1, then... Oh, I didn't really think about that. The cost functions. Oh. Actually, yeah, that doesn't work, does it? I didn't even think about that. That if the cost functions are basically just 1-to-1, then I think actually what you need to do is you can maybe do something like, maybe you find the min element each time, and you update the cost function with this proportion each time. Maybe that's what we're supposed to do. I didn't really think about that. So forget sorting it. You do this. Swap and pop from the back, maybe. You could do that. So you push all these things into this vector, and then you say, so we'll say auto pointer equals standard min element of V. We'll just do just say while true for the time being, or just while not v.empty. Okay. All right, min element of v dot begin v dot end. We're going to use this comparator, and we're actually going to define the comparator each time. Both the cost function and the comparator function will define that each time. And yeah, we'll take m and n, and so we're going to change the proportional change each time. And this is going to be pointer. And what we're going to do is then pop and swap. Oh, this is kind of awkward, huh? just want to see if I can get the basic idea. There's at least a couple of test cases that'll break down if I try to do this approach. So I'm thinking I may need to do things differently. I don't know. Let's see. Does this compile? Let's start with that. Make a compilation error. Okay, that was way too big. It's way bigger than it should have been. What happened? How did we end up? How do we end up here? How does that make sense? Wait, what? Oh, I forgot to pop and swap. Yeah. Okay, I forgot that. If this is the case, then we standard swap pointer with v.end -1 or v.r rend +1, and then we pop back. Does that work? Yeah, I think it's got. I think it's. You can't mix and match reverse iterators with forward iterators. I think these need to be the same kind of a pointer. Or not. Maybe I'm just wrong. I don't know. Not viable. Expects an L value per second. Oh. I don't know. For some reason. Oh, this needs to be an L value. Oh, I think I get it. Okay. Can actually do this. Huh. Can I do that? Actually, I don't know. I don't know if this will automatically convert the back to an iterator. I don't think so. No. How do I convert the back to? Could do something like this. Maybe this works. Excuse me. Oh, okay, that's close. Wow. Hey, that's super close. This is actually just like a more refined version of what we just wrote before, where we just update. There's a proportion each time of m to n. This is very close. Super interesting. So I think the issue is I actually think I know what the problem is. So we got this fly here. It's been here for a while now, a few days. I don't know where it came from. I don't know what food I'm leaving out. It's got to be some filth somewhere that it's feeding off of, which is frustrating because I don't know where it is or what it is. I've been cooking some food in the apartment, so this fly has found his way in. What do we could do? Could do that so we could see it. I want to say somewhere in here there's a 1 and there's a 0, or there's a 1, 1 and a 0, 0, or something that conflicts. Something like that. Now what's really weird about this is I don't think this should be happening. I don't think this should be happening. The reason is that what's really weird about this is, in theory, you get a pointer to something, a min element, right? Pointer. You have zeros and ones for that that element. Then you decrement the zeros and ones, M and N, increment ret, swap this thing to the back, pop the back. Maybe this is getting swapped to the wrong spot. I don't know. What if we set? What if we do this? Still wrong, but what if we do -2? How about that? Does this even matter? Doesn't seem to matter very much. Okay, well that's meaningful. That's that's definitely interesting. What? Ooh, excuse me. Right, so interesting. Okay. Just gives you a dot, dot, dot. Interesting. I don't know. Okay. Maybe we can do this. All right. All right, so let's see, we have 5 elements. You go to v.begin, points to the first element. You add 1, 2, 3, 4. Here, yeah, it should be size -1. I think this is correct. Swap these things, then pop the back. All right, what does this look like? Two zero 15 4 0 23. And you have 1 1 0 2 3 11 0 and 1 1 11 0 0 5. So okay, that looks consistent. Yeah, 0 5 and then. All right, so it looks like we're popping and swapping correctly. I just want to make sure that was correct. Some reason I didn't think this is correct. What's weird about this though is how do we end up with 76 as the optimal? Because a couple of things here. It's actually not possible for, or I would guess that it's not possible for this algorithm to exceed what the correct amount is. Because every element that we select, we calculate it, right? Every element we select, we calculate the zeros and ones, we remove them from the total, the target, and if we don't, it's not sufficient, then we break and we're done. And then we remove that element completely once it's removed. Yeah. It starts off at 0. I don't see how it's possible to. Can create like a. Maybe we can find out what's wrong. It's like I'm thinking maybe this has got something to do with it, but actually it shouldn't. It should just be too small. It should be like not enough. We should sort of terminate earlier than we want. So this sequence, right? And we're going to say we're going to print this sequence at the end. The 75 values. Okay. Okay, zeros, ones, new line, sequence. Okay, so here, before we pop and swap, we want to sequence dot push back centered make pair of zeros and ones. Hopefully this makes some sense. Okay, so it says this is 76. So maybe we're double counting a something here. Maybe that's the problem. Could do a frequency map. That might be better. Actually, I prefer to have do like this style. Style. Should be somewhat consistent. Maybe this. I don't know. Actually, that's a little weird. Okay, so yeah, you can do this. Actually, don't need to include for these programs, but that's okay. Whoa. Whoa. Actually. Hopefully that works. I don't actually know if this, we'll use a regular map rather than a frequency map because I don't want to go write a hash function right now. At the moment, I don't exactly care to. Something very similar to this is what we're going to use to print the frequency map. Okay. Just do frequency pair. We're going to say frequency pair first, frequency pair first, second, and then and this frequency pair second. That's going to look really funky. Okay, what does that look like now? Okay, that's what I thought might be the case. We're just adding all the smallest ones. It's kind of what we're supposed to do. I mean, this is super close. I think we're double counting one of these. I think that's the problem. Because if we take this other frequency map, excuse me. Call it the total frequency. And this is going to be through a V instead of this. And now we can say the other frequency map. Same function, but do that on the total frequency. So if we just split these by, what you'll notice is that there is one extra thing there that's being used that shouldn't be used. So if you go to 1, 1, That's used 8 times here, but it only exists once. How did that happen? Excuse me. Where does this min element, what is this min element operating on? Huh? How do we get 1, 1 over and over again, but we don't get that over here? Here's the actual frequency map as compared to this supposed frequency, this part of the frequency map that we used. So somehow we got 1, 1 a few times, 8 times. How did that happen? I thought something like that was going on, but that's like, how is that even possible? No. What? 8 times? What? Oh, that's confusing. Okay. Do you have you set pointer to the null pointer? Maybe that's what we need to do. I don't think that shouldn't matter. I don't think that would matter. Can we not set this to the null pointer? Nope, doesn't matter. Not even relevant. Somehow, what? I'm so confused. Maybe this is the problem. Maybe this is the problem. That could be it. Actually, it could be me screwing up how the swap is used properly. Yeah, that was my mistake. Messed up how. Yeah, there we go. Okay, I was expecting. I was expecting to be behind one, not ahead one. Right. So I was misusing the swap function there. That's the issue. Yeah, it's swapping what these pointers are pointing to is not the issue. You just swap the not what they're pointing to, but the things that they're pointing to themselves need to be swapped. Right? In other words, these are 2 pointers, swapping the pointers with each other, so they're now pointing at different. They've swapped what they're pointing at. What the pointers are pointing at, that's not what you want to swap. You want to swap the things that the pointers are pointing at. You want to swap those data pieces. It's so confusing. I know. I realize it's like what? It's like the same word, same sentence. One time, in one instance, you're meaning the data that's being pointed to at that address, and in the other expression, you're referring to the pointers themselves, the data addresses that the pointers are pointing to. Yeah, I realize it's super confusing, and that's actually what got me. It's what got me. That's why I was so confused. But yeah, it looks like this is actually one of those cases where there is a better way to do this. Yet to get 75. Yet I somehow missed it. We did use 1, 1, so 49 plus 25. So 48 plus 25 plus 1. And in this case, we did 1 times 1 plus 1 times 48 plus 2 times 25. 99, so 100 minus 99. So we have 1 0 left over, and we had 1 times 1 plus 2 times 48 plus 0, 25 times 0. It's 97. So interestingly, we have 1 0 and 3 1s left over. We could have made this 49, this 1 2. Yeah, why didn't we just take one more of these? I think I know the answer. So here, actually, if we're at the end where the smallest element doesn't work, there could be more than one smallest element that works. And I think that's part of the issue. So we can actually, one more pass, whether there is another minimal element could be used. All right, let's just do it this way. Well, yeah, okay. Sure. Doing something wrong here. Oh, I think I said the problem is. Okay, got it. Okay, destructure. Debug, swap, delete. And we say if, then break. Yeah. I'm going to say found. It's true. Or no, false. And we just say if not found. And we'll break this outer loop. Yeah. This else here is interesting. This is pretty much, yeah, if you're empty. Yeah, it's basically saying that this is empty. If this is empty, then we just exit. Okay, what happens when we do this now? Just search for one last element in case we missed it. There we go, now we're correct. Okay, now I don't necessarily know if this is a correct algorithm or not. I actually have no idea. I couldn't tell you. It looks promising. It looks promising, but not necessarily correct. Something of a heuristic, I guess. Everything that says debug gets a comment. It's commented out. Glory, glory. Bum, 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 no, no. No, 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 no. Now the question, did I make a mountain out of a molehill with this question? That's something we gotta wonder. Did I make this problem out to be a lot harder than it actually is? There's a very good chance of that. Very good chance that the simple greedy algorithm was all that we needed. And I just made this problem way harder than it needed to be. So this is a solid chance of that. Oh, please don't tell me that's what I did. I'm afraid to hit the submit button, but part of me thinks I should because it's going to be hard to find a test case that this fails on. Could concoct one. All right, we could try it. This is going to be interesting. So let's do like 0, 0, 0. One, 0, 1. 10, 1. Something like this. How about that? All right, I think we just go for it. I don't know. There's got to be some case that this fails on. That's just just somehow missed it, I guess. I don't know. I'm gonna just try some random stuff. How about that? We'll do 50-50. 5 and 5. Well, that's actually kind of an easy one. Really, it's just a heuristic that we're using. That seems to be sufficient, I guess. Can we? How about this? I had that test case before that was just like 100 zeros and 100 ones. I don't know, man. I'm not prepared to submit this yet. Like we said before, don't submit it unless you're confident that it's correct, which I am not confident. 1 or 1, 1, 1. Okay. We were saying we need 600. All right, so 300 of each. All right, so we'll get up to, I don't know how to get to 300. 1, 2, 3, 4, 5. All right, we'll go 10. 20. 40. 80. 160. 320. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right? Okay, let's try that. And all right, let's do it a little more mathematically here. 300 divided by 2 divided by 2 to 75. So doubling the, well, we can do 76 or 74 maybe. Let's do 74. Whoops. 2. All right, that doesn't really work too well. What about 30? 76. All right, we'll get to 20. We'll go down to 19. Double a couple times, get to 76. Yeah, we'll try that. Try this again. All right, we'll go 5 of these, right? And then 5, 10, 15, 20. Now we're at 19. 19, 38, 76. Take off 1. 75, 150. And that should be enough, actually. Yeah, that should be it. Okay. Something like this. And now we can do 100, 100. We can do 1, 1. We can do 50, 50. 50, 50. We can do 20, 100. 101. Do 20 and 100. Okay. All right. What does this look like? How long are we doing this for? Oh wow, I've been at this for an hour already. Whoa. Whoa. All right. I don't know, man. I think we just go for it, because there's got to be something I missed, but there's almost certainly a test case that I don't handle properly. But I'm so like, I don't know, man. All right, I think we go for it. Just because it's going to take me a while to figure out the test case that we've missed. But there's some test case somewhere that we missed, definitely, almost certainly. Could we do like 1, 1? Oh, okay. So they all have to have at least 1 already. Like, if this is correct, I can't believe it's correct. That's kind of the problem I'm having here. It's kind of the issue I'm having here, is I'm like just in disbelief. All right, let's go for it. I don't know. That's something it had to be something I missed. It has to be. Yeah, there we go. Okay. That's kind of interesting. I probably could have came up with that one, but I don't know. It's hard. It's hard. It's just hard. Yeah, there's got to be something. Just looking at it like, man, this got to be some test case somewhere. Because I know this is not like an exhaustive search. This is just like a heuristic approach. It's pretty good, or it seems pretty good. But it's not necessarily, as I was saying, it's fast, but it's not correct. Or at least I wasn't able to prove it was correct. So this is interesting. The cost function for 6 and 6, it's, everything has the same value. So this 4 is the least valuable. Yeah, this is the least costly. And then, but then you can select these two. So you could have picked these two and used the resources more effectively, more efficiently, even though the cost was less for this. Look at that. Wow. Wow. That's annoying. I think this is why you need to use an exhaustive solution that you know is correct, even if it's slower. I knew there was something. Like I knew it because I have no way of proving that this is correct. I think it's correct in most cases, but not all of them. Yeah, that's a good example. Now, how can you correct this case? You kind of can't change this to handle this case and also other similar cases, because basically what this is saying is that simply finding the minimum cost each time isn't going to give you the optimal, because it's not I'll shave my mustache here. Let's get it into my mouth. Yeah, simply picking the minimum cost each time isn't going to do it, because also, wow, I'm really tired. Simply taking the minimum cost each time isn't going to do it, because you could end up, well, for among other things, you end up in this situation. But it isn't necessarily the most efficient use of your resources. That's kind of what that comes down to. Because technically a more expensive usage of your resources to go in one direction allows you to go in a different direction, which is also very expensive, but is just right with respect to the resources you have. Whereas if you go in like the more balanced direction, then you can't go into either of these directions. Which I think this is kind of unusual. Like I said, I think this is like a minority of the cases. I think otherwise you have a pretty good heuristic, but there's no way to rectify this easily, because you basically have to remove one of the previous. You kind of need to do some backtracking, basically, which is like. Excuse me. Just somewhat not ideal, I guess. You can maybe write a more balanced algorithm here by using part of the heuristic and part of the backtracking algorithm. What you can also do alternatively is go for. There is another solution that I was thinking of, so I'm kind of a little bit disappointed, but not too disappointed. I kind of knew that this might be the case, that this would be probably not correct, but very fast. There's this thing called longest increasing subsequence, and what I'm looking to do is apply CP algorithms here. What I'm looking to do is to apply a similar approach to this problem, to the longest increasing subsequence, and use something similar to this to solve the problem we're looking at now. To use a dynamic programming solution. Like I said, it might be too slow, though. That's the thing I'm kind of concerned about. I think it might not be. I'm pretty sure it's correct, but it may be too slow is the problem. Yeah, so let's add this to our list of things we need to test. Excuse me. I'll try to explain what this solution is going to look like. All right, so I take it back what I was saying about this problem being easier than I'm making it out to be. I think this problem is quite challenging. We're going to delete all this. We don't need all this. Some of it we can keep, but for the most part we don't. Okay, so the algorithm, the idea that I had goes like this. You have, excuse me, you have three variables you have that are going to be moving, or that are going to be changing value over a range. The first is, we'll call it x, which is the number of zeros to consider. The second variable is the number of ones, we'll call that y. The third variable is going to just be s, which is the size of your set, so the number of subsets, or yeah, a number of strings that you've considered up to this point. And what we're going to do, the dynamic programming part, is that we're going to say, we're going to start at 0, 0, 0. So empty set, no ones, no zeros, nothing, just empty. And we're going to say, okay, loop over, and we're going to use a bit set also associated with each. The bit set's going to represent which sets have been considered. So that way when you look to consider other sets, you don't consider the sets you've already considered, if that makes sense. So like if you have something with 5 sets already in there, you're not going to look at the sets you've already looked at. You're going to pick new other sets. So that's the purpose of the bit set, is it's going to be 600 sort of bits in a bit set, and just going to flip them on and off depending on which sets we've considered. In the worst case, 600. So the idea is that from 0, 0, right, we're going to loop through all of the sets for that particular entry, 0, 0 entry, and we're going to say, okay, let's add the particular set that we're interested in looking at to this set. So for each bit, we're going to add it and see, we're going to check two things. So is that, if it's a new, so we're going to increase the x and y values based off of the subset that we're adding, or the string that we're considering, right? The string is going to be reduced to just the number of x, number of y's, or the number of zeros, number of ones. And we're going to add, we're going to say, so like for one set we have 1, 2. So we add to 0, 0, we add 1, 2. Now we consider 1, 2. Well, in our matrix, we're going to say, okay, if there's no entry at 1 and 1 set, right? So it's sort of a pair 1, 1, kind of like a pair 1, 1. 1 pair and 1 set. So it's going to be sort of like a triple three-dimensional matrix, almost, something like that. But not exactly two-dimensional. Really, the 2 dimensions are just going to be, the first dimension is the I value, and the second dimension is going to be the number of sets. Yeah, the number of strings considered at that point. So one string considered, and we say 1 is the value for x, or for I. And then you would say, okay, if there's nothing there in the matrix yet, we could use an unordered map. So it's a little bit more, so it's not exactly, you can use an unordered map so that it's relatively easy to check whether or not something's been added there or not. I mean, you could use it in a matrix, but it also saves on how many elements to consider too, somewhat. But it may be faster to use a matrix, by the way, just because the way matrices, they're just faster to operate on than I think unordered maps. Unordered maps have hashing involved, and they also have other operations, which I think it might actually be a lot slower to use a hash map. But that's yet to be seen. If it's too slow using a hash map, then we'll switch to a matrix, and hopefully that'll be fast enough. But in any case, we can say, yeah, so we check that spot. We say, is there something there or not for that set number, yes or no? If there is something there, then we're gonna take the maximum of the two y values to consider. So the maximum of the number of ones. I think we said y's are ones. So the maximum of the number of ones. So if there's nothing there, then we just write there. So we would write to one set x value of 1, we would write a y value of 2. And if there was something there, let's say there was a 1, 1 there, so it was 1, 1, 1 all the way across the board, then we would say, well, 2 is larger than 1, so now we're going to update that to 1, 2 with one set. And we're also going to update also contained in that information is the bit set that corresponds to this value. So we're going to also change that to the correct bit set, update that to the correct bit set. Yeah, we're going to do that at each point. So there'll be sort of a pair of numbers, I guess, a bit set as well as a bit set as well as a value. And then what we're going to do is consider the next round of sets. So now we say, okay, of all of the values in the set with set 1, those pairs of set 1, we're going to now consider those values of set 1. We're now going to consider adding another set to each of those. So again, we go through each of their bit sets and try to flip a bit and see if we get something new. So it's dynamic programming, but it's also kind of an exhaustive search as well. And each time we're just keeping the values of x and y such that for each value of x, there's some maximal y value at each sort of set size. And we're going to maintain the bit set required in order to kind of figure out which sets we have added or haven't added for each pair, or for each number, each entry. So the point of all of that is once this has been done up to a certain point, we're going to eventually hit a point where we're actually exceeding. It's going to be the total number of the total n and the total m and total m, so the total number of zeros and the total number of ones. If you decrement those values by the given m and n, what we're looking for is kind of a mirror image or a reverse image where we're trying to find actually the largest, the smallest size set that will exceed the amount of resources determined by taking that total minus the target. And the idea is that if we can get a subset on that side, on the other direction, where it's a smallest subset that uses the most resources, then the inverse of that must be the largest set that uses the given resources, the limited resources. So it's kind of a sort of solving the mirrored problem. And with that in mind, then we have a terminating condition for how many sets as soon as you find a pair of x and y values that exceed the targets, the new targets, then you can stop right there, right? You're kind of done. You've done enough searching because you weren't able to find that with the previous set, so there's no set smaller, and then you did find it with this set, and then you just take the difference between the total number of sets and that value, and that's your solution, right? Because the inverse subset set of subsets is or the inverse subset of strings is actually one of the sets that satisfy the solution. So that's the idea in English. Kind of complicated to describe, but it's something very similar to the longest increasing sequence. It's similar, but it's not the same, but it's similar. And yeah, I think I'm gonna lay down now. Some problems we're gonna run into is like implementing this so that way it's fast enough. I don't know if this is it's not gonna be particularly quick. I think the way this is set up, I think it's gonna be kind of slow. The idea, so I'm a little bit concerned about that. I'm kind of afraid that if I implement it, it's gonna be too slow, and that'll be disappointed. I definitely want to lay down for a minute or two before we, implement this. But it's definitely unusual, I would say. It's a kind of dynamic programming solution, but as I said, definitely more on the unusual side. Not something I would think up, definitely not something I would think up on the spot during an interview. I think if I got this question during an interview, I would just fail. That would just be it for me. It's too complicated. It's too difficult to realize, to think up. Oh, I don't think this is necessarily a hard level difficulty, but it's definitely extremely challenging. Or challenging. I would say extremely challenging, but just challenging. Excuse me. I don't know, man. When you're dealing with combinatorics, it can get pretty complicated, pretty difficult, pretty quickly. It's kind of what we're dealing with here, is a different kind of combinatorial backtracking type of question. What I want to do, I kind of want to stop the stream here, lay down, go to the bathroom, maybe take a nap, and then come back and try to implement this idea that I had. This idea that involves this idea that I had this involves some dynamic programming. I wonder if just thinking. I'm sorry. I'm just thinking here. I wonder if I'm wondering if I can do this with just arrays and not use an unordered map. Well, part of the problem is we don't know how far. Oh yeah, there is another issue too. There's another piece that I forgot, which is actually you want to switch things in such a way where you want to minimize. Excuse me. The quote-unquote x coordinate is supposed to be minimized. So if you have way more zeros, or even just more zeros than. Oh, okay. That caught me off guard. If you have more zeros, no, okay. So depending on m and n, if m and n are not equal, then the value that you want on the, I guess on the input parameter to your map, to your keys, you want that to be the smaller of the values. And the reasoning is because the other value, you kind of aren't keeping very much information related to that, because it's just whatever's keyed off. You just take the maximum. You just always maximizing the keyed off value or the other value. So it doesn't really affect the computation. So you'd want the larger of the two. Now, like I said, they could be equal, and then it doesn't really matter that much. But fortunately, it seems that if they are equal, the amount of processing that you have to do is relatively low. Yes. Is that right? It's 100 string. No, it's 600 strings. Is that right? 300? Is it 300 strings or 600 strings? I think it's 300 strings. 300 strings. I have to double check that actually. It's 300 or 600. I want to say it's 300. I don't think it's 600. Let me check right now. Excuse me. Oh, before I make too many assumptions about this. I'm pretty sure it says 300, but maybe it doesn't, and I'm just thinking things. 600 is 600. Oh boy. Oof. Okay. Yeah. So if it's 600, you can do half of them are zeros and half of them are ones, and so you have 300 by 300. 50 of them. Yeah. Well. Yeah. So if you have 100, if you have 50-50 times 600, that means you have 30,000 each. So you're stuck with 30,000 strings, and so your your value could go all the way up to 30,000, right? Adding all these together. Excuse me. Fortunately, M and N are relatively small, but actually going this other direction, we would need to consider, like, we actually would have a very large set. I think we'd end up considering, but nevertheless, or nonetheless, that 30,000 as a I was doing this math before earlier. How did I figure this out? That 30,000, you really can only get from 1 to 50 and have unique values, I guess, for I. Excuse me. I guess what I mean to say is that if you want like a range that's sort of total, I'm actually not sure now. I don't know. 30,000 different numbers between 1 and 50, more or less. Could actually be, it could range more than that. Could be from 1 to 100. However, the problem with that though is there's a possibility of throwing off the balance, so to speak. But I guess you could just have a reciprocal string, all zeros and all ones, and then the total balance is not thrown off. And so you can get, from 1 to 100, and then add to 1 again, 1 to 100, and then add to 2, I guess, or 2 or 3, what have you, from 1 to 100, so you end up with 100 as the largest value, then 200, and 300, etc., etc. And that can go all the way to 30,000. And then you're multiplying by 30,000 at the end, times 600, right? Each step at 600 possible new things to consider. No, hopefully by the end there, that bit set would just be like 1 or 2 sets, and it wouldn't actually be 30,000. You know, it wouldn't actually have to go through all one to 30, 0, 0 to 30,000 or 1 to 30,000. Shoot, yeah, I don't know. I don't think this algorithm would work or will work. This makes me think that the problem is don't necessarily know what the problem is, but I know oh man, sorry, I'm kind of falling asleep here. My thoughts are a little bit varied, I guess. Maybe I should just go. Forgot what I was thinking about or talking about. Yeah, I guess finding it. No, it's not it either. Let me ponder. I think this is going to be too slow. That's the problem. Even if I use an array. Hmm. Hmm. Okay. Oh boy. Oh man. Alrighty. I think I'm gonna stop there. Take a break. Cut it here. I've just been thinking about this and thinking about it. And I think it's time to take a break. Yeah. I think the idea I had works. It's just, I think it's going to be too slow. 600 times 30,000 is a lot. Yeah. Um, yeah, I'm ready to fall asleep here. 600 by 30,000, that was a lot. That's 1.8 million. Oh boy, I'm falling asleep. Oh man, no kidding. So performing 1.8 million. Hmm. I think this might be too expensive. Hmm. All right, like I said, I should take a break. I'm like falling asleep as I'm looking at this. I think it's too slow what I'm trying to do. No. Okay. Hmm. 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 Um. Hmm. I don't have a solution to this. Oh man. Hmm. I think at this point we're just gonna take a break. As I said, it's like I can't seem to think of a seem to think of a way. Like I think any way I look at it, that algorithm that I was just describing, it's too expensive to actually write it, to actually perform it. In terms of the amount of the runtime. Um, I don't know why before I was thinking. Excuse me. I don't know why before I was thinking that we could do this in a lot less than 30,000 for the value, but I don't think so. I think 30,000 is good as. I think 30,000. Yeah, I think we have to have a map. So our map is going to be ranging values up to 30,000, and then part of the issue is wondering if just a heuristic plus some backtracking in. Hi friend, hello Melito. Welcome back, hello, hello. Forgive me I didn't respond for 10 minutes, I'm kind of falling asleep over there. Happy birthday, I think I noticed that. It says your birthday is tomorrow, so happy birthday. Yeah man, I have an idea for another solution, but I think what I'm going to do is I'm going to probably end stream here and then come back to this and try the other approach. For some reason I thought the other approach was easier. It's actually pretty rough. It's yeah, 600. They could be 50 each. 30,000 could be the total. For some reason I thought only 50 times or 51 times 25 would matter. I don't know why I thought that. That's not correct at all. Um, that each step we'd only need to consider 1,000 at a time. I don't think is correct. Well, actually, maybe that is fine. Actually, maybe I'm wrong. Maybe I'm wrong about that. Maybe I could use a matrix that goes up to 30,000, but only roughly 1,500 each step would matter. And then even 600 would be more like 300 in the average case. Excuse me. Yeah, I don't know. I think actually when I implement the algorithm, it'll probably be a little bit faster than I realize. I think I do need to use matrices instead of or fixed vectors instead of hash maps or maps. Let me go. I'll come back. I'm just gonna go to the bathroom, lay down, just take a nap. Probably come back, stream a little bit later today, and then work on this solution. Yeah, I mean, I don't really have anything better than that. That's all I got really for this problem. It's that last idea, and it might work, maybe not. It's sort of a dynamic programming solution. Hopefully it works. We'll see. If that doesn't work, I'll probably just check out the discussion, see what I'm supposed to do. But yeah, all right. Like I said, let me go. So yeah, thank you again for watching. I'll talk to you all soon. Have a good rest of your day. I think I'm going to try, see how I feel, because I'm like just really tired. End stream here, take a break, then come back, write that dynamic programming solution. Hopefully it's fast enough to solve the test cases, and then hopefully it's fast enough for the solution. But if it's not fast enough, then hopefully it's correct too. I actually don't know if it's correct. I think it's correct. But yeah, all right, let me do that. So thanks again. Thank you again.